Good morning. Welcome to this day about regression analysis. So I put together a content like this. Two main headings here, simple and multiple regression analysis. Simple, we have one independent variable. Multiple, then we have two or more independent variables. And always we only have one dependent variable. Well, I don't think I go through this. I'll jump straight into it. So simple regression analysis, as I just said, we have one dependent variable and it has to be continuous. Because we're going to talk if the values on the dependent variable increase or decrease when the values on the independent variables change. So we have to be able to talk about increase and decrease. And on variables on nominal scale, we can't speak about increase and decrease. So you can't have a variable that is nominal scale as a dependent variable in this kind of linear regression. The independent variable might also be continuous, because also there we're going to speak about what happens with the dependent variable, what happens with the values on the dependent variable when the independent variable increase. So we can't have a nominal scale variable as an independent variable in regression analysis, with one exception. Dichotomous variables can be used as independent variables in regression analysis. If we have sex, for instance, and let's say we call men 0 and women 1, then we'll calculate what will happen with the value on the dependent variable when sex increases from 0 to 1, which is the same thing as analyzing what is the mean difference between men and women on the dependent variable. So it's the same thing as the independent samples t-test. You get the same results. So dichotomous variables could be used as independent variables in a regression analysis. Preferably not dichotomous dependent variables. Although you get some kind of results. It's interpretable. However, we prefer to do logistic regression if we have a dichotomous dependent variable. The dependent variable is quite often called also the outcome variable. And independent variable is quite often called predictors. So we predict how people, what value they have on the dependent variable, on the outcome variable, from what value they have on the independent variable, on the predictor. So let's, for instance, say we have data like this. We have data from five individuals. And we have how much therapy they have received. Let's say they all had depression, and now they have received therapy, differing amounts. So occasions they have received therapy. And after that, we measure the life satisfaction on a scale from 1 to 7. So we get data like this. And now we want to see if we can predict life satisfaction from amount of therapy. Is there any effect? Is there any association between therapy and life satisfaction? And if we plot our data, it looks like this. And then we try to represent this association with a straight line. So far we're talking about linear regression. So we're going to represent our data, our association with a straight line. So I put a line there. And you can do it completely at random. No, you don't do it randomly. You put the regression line, this is called the regression line, in order to fulfill something. Namely, you want those distances to be as small as possible. So the regression line is placed so those distances are minimized. And what are those distances? Well, according to our regression line, people have this level of life satisfaction for the various levels of therapy. So according to our regression line, if you have 3 occasions of therapy, then you're predicted to have this level of life satisfaction. If you get 2 occasions of therapy, you're predicted to have that level of life satisfaction, and so on. So the line represents predicted level on the dependent variable for various levels of the independent variable. But now we see, for this person, for instance, he or she is predicted to have this level of life satisfaction, but actually he or she has that level. So we make a false prediction here. Our prediction misses the actual value. So we have a difference here between observed value on the dependent variable and predicted value on the dependent variable. What do you think that difference between predicted and observed values is called? Residuals. It's the residuals. Do we like residuals? No, we hate residuals. We would like to rid the world of residuals. I'll be in the next EU election, and that will be my slogan. Let's get rid of residuals. And nobody understands what it says, but it sounds good. I vote for him. Okay. So we place the regression line in order to minimize those residuals. So we minimize this formula. For every value, for every individual value on the dependent variable, we take the value minus predicted value. So the y with the roof on top here, it's the predicted value. So we take the difference between actual value, observed value, and predicted value. We square that, and then we take the sum over all individuals. Sum of squared residuals. So the regression line is placed in order to minimize the sum of those. How do we get a line that minimizes those values, the sum of squared residuals? Well, the regression line is a straight line in linear regression, and a straight line has this formula. Y is A plus B multiplied by X. Okay, that's the formula for a straight line. A is the intercept. And what is the intercept? The intercept is the predicted value on the dependent variable when the independent variable equals 0. It's where the regression line crosses the y-axis. So that's the intercept. And of course, the y-axis represents value 0 on the independent variable. So what kind of value do we predict individuals to have on the dependent variable if their value on the independent variable is 0? That's the intercept. B in this formula is the slope. Slope of the regression line. And the slope is also how much the value on the dependent variable is predicted to increase when the value on the independent variable increases by 1. That's the slope of the regression line. So if the value here increases from 1 to 2, how does the value on the dependent variable, how is it predicted to change? If you go from 2 to 3 and so on. Of course, it's the same because it's a straight line. So the slope of the regression line. How much the value on the dependent changes for an increase in the independent by 1. It's also called, it has many names, it's also called B here, the non-standardized regression coefficient. All those 3 things is the same. So how do we calculate the regression coefficient, the slope of the regression line, in order to minimize the sum of squared residuals. Well, I'm not going too close into this, but we could use a formula like this, for instance. So we take the ratio between the standard deviations of the dependent and the independent variable. We take the ratio of those and we multiply by the correlation between the independent and dependent variable. That will give us a regression coefficient that minimizes the sum of squared residuals. The value on B here, the value on the slope, the non-standardized regression coefficient, is affected by unit of measurement. So if I take real data, I had an example here. I take real data where I have people's height and their weight. So if I predict weight in kilos from height in centimeters, I get the regression coefficient of 0.9. What does that mean? How do we interpret this regression coefficient 0.9? What does it tell us? In the adult Swedish population, what do we know about this adult Swedish population? For an increase in height with 1 centimeter, we expect an increase in weight with 0.9 kilos. So you get this picture in your head. If you take a bunch of adult Swedes and you slice them in 1 centimeter thick slices, those slices will on average weigh 0.9 kilos. It would be a funny question in Trivial Pursuit. That's what it says. If I take the exact same data, but I change weight from centimeters to meters. So I predict weight in kilos from height in meters. What regression coefficient do we get? What non-standardized regression coefficient do we get? 90. For in the adult Swedish population, for an increase in height with 1 meter, we expect weight to increase with 90 kilos. So the value of the non-standardized regression coefficient is affected by unit of measurement. So what do we learn from this? Well, we learn that you can't have a look at the non-standardized regression coefficient and say, oh, it's a strong effect, or oh, it's a weak effect. It doesn't tell you that. So if the regression coefficient, non-standardized for a certain variable, for a certain independent variable, might be 0.00001, and another one has the non-standardized regression coefficient of 269,000 million. It might still be that the association between the first independent variable and the dependent is stronger than the association between the second independent variable and the dependent. It doesn't tell us really so much about the strength of the association. Of course, if they are on the same scale, the independent variables, it might indicate the strength of the association. But if they're not, it doesn't. So that's how we could calculate the value of the regression coefficient. So how would we calculate the value of the intercept? Well, if the formula for the straight line is like that, y is a plus b multiplied by x, with some algebra, we take the a out here. A is y minus b multiplied by x. Okay. And then there is a rule here. The regression line always, I hope I'm not saying wrong here. No, say always again. The regression line always goes through a certain point. Namely, the mean of the independent variable and the mean of the dependent variable. The regression line always goes through that point. So if you get the information, this individual has a value on the independent variable that equals the mean on the independent variable. What value will you predict that this individual has on the dependent variable? You don't even have to know anything. You don't even have to know what variables they are. What will you predict? This individual on the dependent variable will have a value that is the mean on the dependent variable. From the mean, you will always predict the mean, because that point, the regression line always goes through that point. So if we put in the mean here, the mean on the dependent variable and the mean on the independent, we can calculate the intercept if we have calculated the value on the regression coefficient here. Okay, let's take our example here. So the mean on therapy, 3. Mean on life satisfaction, 3.4. Standard deviations, 1.6 and 2.3. And the correlation here, 0.9. Of course, you usually don't have correlations as strong as that, but with this example. Okay, we calculate the regression coefficient here, 1.3. And we can calculate the intercept, minus 0.5. So the regression coefficient here, 1.3. What does it tell us? If amount of therapy increase by 1, what will happen? What do we predict will happen? Amount of the degree, the level of life satisfaction on the scale from 1 to 7 increase by 1.3 points. That's what it tells us. And the intercept here, minus 0.5. What does it tell us? If you don't get any therapy, your life satisfaction is predicted to be minus 0.5 on a scale from 1 to 7. You have really, really low life satisfaction. Does it make sense? No. We outside the scale. And that happens quite often. So what do we learn from this? Well, we learned that the intercept, quite often it's not sensible. And in this case, what range of values on the independent variable have we used in order to calculate our regression coefficient, our regression line? Well, the range is from 1 to 5. And what we get is a regression line that hopefully functions quite well within this range. But we can't be sure. Well, we can't be sure that the relationship, the association between therapy and life satisfaction remains the same outside this scale, outside this range. Well, actually, we can be pretty sure that it will not continue in the same fashion. Because if you see we're up there, the predicted value, if you get 5, we're up at about 6. It can't increase much more than that, because 7 is the upper limit. So we probably have some kind of S-formed association here. You can't, we're down at below 1 here already, and you can't go below that. So probably the real association is some kind of S-form.
Not linear.
It's not linear, but the regression line is linear. So we can't be sure it makes good predictions outside of the range that have been used to calculate the regression line. Yes, imagine we had one individual here with 0 therapy. And this person would have, let's say, 1 in life satisfaction. There's a dot. How would it affect our regression line? Yes, it probably would. it would probably make the regression line, the slope, lower slope. And in that case, we would get what would happen with the intercept. If you decrease the slope, what would happen with the intercept? It would increase. I'm not sure it we would get a sensible intercept anyway, but it would be at least higher than we have now. For instance, with my data, if I have height and weight in adult Swedish population, well, if I remember right, intercept was negative. What does it say? It says that if you as an adult Swede have 0 centimeters high, if you're 0 centimeters high, you will weigh like minus 20 kilos. It's because it interpolates to values that doesn't really exist on the scale. Let's imagine we do the following. We standardize the independent and the dependent variable. Zeta standardized them. What happens with a variable if it's zeta standardized? What characteristics does it get? We know two things about zeta standardized variable. Mean is 0 and the standard deviation is 1. So it always has those characteristics. So let's zeta standardize the independent and dependent variable. And then we do the regression analysis. We calculate the regression slope. In that case, the slope, the regression coefficient, is called beta. So it's a standardized regression coefficient. If the independent and dependent variable are standardized, what regression coefficient would we get then? And before, the regression coefficient stood for what change do we expect in the dependent variable in units of measurement when the predictor increases by 1 unit. What does it say now? If the standardized independent variable increases by 1, what does that mean? An increase by 1 is the same as an increase by 1 standard deviation. So the beta coefficient stands for how many standard deviations do the value on the dependent variable change when the independent variable increase by 1 standard deviation. So the unit now is always the same. The unit is standard deviations. And the nice thing with this is that this is not affected by unit of measurement. If I predict weight from height in centimeters or from height in meters, doesn't matter. The standardized regression coefficient will be the same. Therefore, the beta coefficient here can be used to compare associations. So if one independent variable has a beta coefficient that deviates more from 0, that independent variable seems to have a stronger association with the dependent variable compared with some other independent variable that has a beta coefficient that deviates less from 0. So the more the beta coefficient deviates from 0, the stronger the association between the independent and the dependent variable. Sometimes it's said, I said it many times myself, I guess, that the beta coefficient falls within the same range as correlation between -1 and +1. But actually in some cases it can be outside of that range. When I see that, it makes me a bit uncomfortable. But it can happen. And I read the texts that said that, well, it happens sometimes. Don't get too nervous about it. It happens sometimes. But I still get a bit nervous when that happens. if we standardize the independent and dependent variable and do a regression analysis, what intercept do we get? And you might think, oh, how can we know that? Well, we can know that. What point do the regression line always go through? Mean, mean. And if those variables are standardized, that means 0, 0. So the standardized regression line always goes through origo. So the intercept is 0. So we don't get a standardized intercept. Of course, usually we don't want only to calculate the regression coefficient in our sample. We want to estimate what the regression coefficient might be in the population that the sample is representing. So we want to significance test our regression coefficient. And in order to do that, we calculate a few things. We calculate something called the standard error of estimate. And it's given by this formula. We take every value on the dependent variable minus predicted value, square that, divided by degrees of freedom, and the square root of that. Does that formula remind you of something? It's not completely the same, but yeah, it's pretty close to the formula for standard deviation. Standard deviation. How much individual values on average deviate from the mean? This is instead how much, it's not completely true to say like this, but approximately true. And that's our business, to deliver approximate truths. So it's the average difference between observed values, actually observed values, and predicted values. So it's close to, it has similarity with the standard deviation. We're going to calculate two parameters. We're going to use our data to calculate two parameters, the intercept and the regression coefficient. So it fits with that. So if you have only two individuals, you can't calculate the regression line, because you can always draw straight lines through 2 points, and you don't get any residuals, and you can't do the calculation. You need data from at least 3 individuals in order to be able to calculate this. So it's not completely true to say this, but it's pretty close to how much the predicted values on average miss the actual observed values on the actual scale of the dependent variable. Do we like this standard error of estimate? How do we want it to be? Small. Because of course we want to do good predictions. So the deviation between predicted and observed values should be small. So we want this to be small. What did we do when we conducted the t-test? Well, for instance, we changed the standard deviation to standard error instead. Here it's actually called standard error already, but it's more like a standard deviation. But from that we can calculate a standard error of the regression coefficient with this formula. So we take the standard error of the estimate and divide it by standard deviation on the independent variable multiplied with the square root of sample size minus 1. That gives us a standard error for the regression coefficient. We came across standard error before, standard error of the mean, to be more specific, when we calculated t-tests. Standard error of the mean. What did the standard error of the mean tell us? What kind of information did it give us? How much sample means on average or estimated to deviate from the mean in the population. The average deviation between sample means and the population mean. What do you think this standard error stands for? Is an estimation of? No longer a standard error of the mean, but instead a standard error of the regression coefficient. So what does it stand for? What does it estimate? How much sample regression coefficients on average are predicted to deviate from the regression coefficient in the population that the sample represents. It's the same thing, but for regression coefficients instead for the mean. Because of course you have a population, you have the independent variable and dependent, and you can calculate the regression coefficient in that population. If you draw samples from this population, the regression coefficient calculated in the samples will usually not be exactly as the same as the one in the population. They will deviate more or less from the population regression coefficient. So this is an estimation of how much the regression coefficients calculated in samples on average will deviate from the regression coefficient in the population. So what do we do now? We do a one sample t-test. So we calculate, this is our regression coefficient in the sample. We can take -0 if you want to. So we have a look at how many standard errors our regression coefficient deviates from 0. So we test our regression coefficient towards the value 0. Why do we test against 0?
This is the point of no relationship.
Exactly. If the regression coefficient in the population would be 0, that means there is no association between the independent and dependent variable. So what is the null hypothesis here in regression analysis? The regression coefficient in the population is 0. That's the null hypothesis. And now we want to calculate what is the probability of getting a regression coefficient that deviates this much from 0, as our regression coefficient does, this much or more, if the regression coefficient in the population would be 0. And this we calculate by having a look at how many standard errors our regression coefficient deviates from 0. That's what the t-value stands for. How many standard errors do the regression coefficient deviate from 0? The more standard errors our regression coefficient deviates from 0, the more this t-value deviates from 0, the lower is the probability of getting our data if the null hypothesis is true. Just as before. So we can transform that t-value to a probability. Probability of getting our data if the population regression coefficient actually is 0. Okay, let's take our example here. So we can calculate residual sum of squares, 4.3. Standard deviation on the therapy variable here, 1.6. We calculate the standard error of estimate, 1.2. It's not really true, especially when we have a small sample like this. But, well, somehow, how large those deviations are on average. On the scale here, that life satisfaction is measured on. Something like that. We take that value and transform it to standard error of the regression coefficient. Then we take our regression coefficient that we have calculated to be 1.3 before and divide it by the standard error, and we receive a value of 3.4. So where is our regression coefficient 1.3? Where is it located? 3.4 standard errors. Yes. It's located 3.4 standard errors above 0. We could compare that with, if we look at the t-table, for instance, if we go for the significance level 0.05, and in this case we have 3 degrees of freedom. We have it there. It's number of individuals minus 2 in this case. Or more general rule is number of individuals minus number of predictors minus 1. So in this case, 3 degrees of freedom. And here it says 3.2 would be the value we get from the t-table. What does that tell us about samples of size 5? Sample of size 5. Okay. Samples of size 5. You have a population. Doesn't matter which population. You draw a sample from that randomly, a sample from that population. A sample with 5 individuals. In that sample, you calculate the regression coefficient for the association between 2 variables. Doesn't matter which. Okay. You calculate the regression coefficient. This value here gives us the information that regression coefficient calculated in a sample of that size will, with 95% probability, deviate less than 3.2 standard errors from the population regression coefficient. With 95% probability, the regression coefficient calculated in the sample will be within 3.2 standard errors from the population regression coefficient. So if the regression coefficient in the population, for instance, would be 0, the regression coefficient in the sample with 95% probability will deviate maximally 3.2 standard errors from 0. How many standard errors did our regression coefficient deviate from 0? 3.4 standard errors. So what is the probability of getting that, a deviation this large, if the population regression coefficient actually would be 0? We can't say exactly, but we can say it's less than 5%. The probability of getting this, if the null hypothesis is true, is less than 5%. So what conclusion do we draw from this? Do we do it with a null hypothesis? We throw it in the bin. And instead we say what? In the population, there is a significant relation between the independent and dependent variable. In this case, amount of therapy and life satisfaction. Should we say something more? We should not only say there is an association, we also say it's a positive association. The more therapy, the higher the life satisfaction. Our regression coefficient deviates significantly from 0 in the positive direction. So we assume the regression coefficient in the population is above 0. There is a positive association. A bit about wording there. You said we assume that in the population there is a significant association. I would prefer to say it is the word significant, non-significant you use about samples. You calculate if something is significant in a sample. In this case, we calculate if our sample regression coefficient deviates significantly from 0. If it does, we have a significant result in our sample. Then we assume that it looks in a certain way in the population. In this case, we assume that the population regression coefficient is above 0. Did you follow that? Significant, non-significant, those expressions we use about parameters in samples. If it's significant, then we assume it looks a certain way in the population. Okay, if you didn't follow me, no, it's not a big thing. Let's be a bit philosophical here. Have you heard this expression, regression towards the mean? I haven't read the original text, but it's usually described Francis Galton, who is famous for a lot of things, mainly that he was the cousin of Charles Darwin. Well, he seems to have been very active in many areas. What does it mean, regression towards the mean? Well, it means that things tend to change. A lot of things doesn't remain stable, they change. And they don't change randomly. They change towards the mean. If you wake up one morning and you feel really bad, be assured you will probably feel better the day after. You regress towards your personal mean. On the other hand, if you wake up one morning and you're in a brilliant mood, be sure you will feel worse the day after. If you throw a dice and it gives you 6, you probably get lower value on the next throw. If you throw a dice, you get 1, you will probably get a higher value on the next throw. Things tend to change in the direction of the mean. I think it's usually said that Galton observed this about the association between fathers and sons' height. He saw that tall fathers tended to have tall sons, but not as tall as themselves, while short fathers tended to have short sons, but not as short as themselves. So there was an association, but there was also a regression towards the mean. And this does not mean that everything eventually will become equal. It doesn't mean like that, because it functions the same way in the backward in history. If you wake up one morning and feel really bad, well, you probably felt better the day before. If you wake up, you feel in a brilliant mood, you probably felt worse the day before. So the regression towards the mean functions both towards the future and backward in time. So how does it come into this regression analysis? Well, we have a formula here. The regression coefficient. Correlation multiplied by the ratio of the standard deviations. Okay, so let's say we have association that looks like this. Okay, and we calculate the regression line. Let's say it's there. And then we use this regression line in order to make a prediction. So we have an individual who has that value on the independent variable. Then we'll predict that he or she will have that value on the dependent. Right? Let's change a thing here. I'm not sure I succeeded, but let's keep the ratio between the standard deviations intact, but we decrease the correlation. We do like this. If we decrease the correlation, keep the ratio of the standard deviations intact, does something happen with the regression coefficient? We kept that intact, but we went from 0.9 to 0.7 in correlation. The regression coefficient decrease. How does it affect the regression line? It becomes, I don't know how to call it, less steep, flatter. Do you say like that? Doesn't sound good. Flatter, it becomes, do you have a better word for that? It becomes less steep. What is less steep? Well, it becomes less steep. It becomes less steep, like this. What point is that? Mean of x, mean of y. Because that point the regression line always goes through. If we now make a prediction, now we have an individual with this value on the independent. Will we make the same prediction about the value on the dependent variable? No, we adjust the prediction. Now the predicted value would be that instead. Right? We adjust the prediction. In what direction? In this case, lower. But is it always lower? Now let's imagine we have an individual in this end instead. Before, we would have made that prediction. But now we make instead that prediction. So we adjust the prediction in the direction of the mean on the dependent variable. If the association between the independent and dependent variable becomes weaker, we adjust our predictions towards the mean of the dependent variable. Does that sound sensible? A sensible thing to do? We could express it like this. When we make our prediction, we take two things into consideration. The value on the independent variable of a certain individual and the mean on the dependent variable. The stronger the association is between the independent and dependent variable, the more our prediction is affected by the value on the independent variable, and the less it's affected by the mean of the dependent variable. The weaker the association is, the opposite happens. The weaker the association, the more we ignore the individual value on the independent variable, and the more the prediction is affected by the mean of the dependent variable. Does that sound sensible? It sounds very sensible to me. Because what does a weak association mean? Well, it's a lot of means here. It means that the information you get about what a value an individual might have on the dependent variable, given that they have a certain value on the independent, the less information you get from that. And the more we ignore that, because it's less informative. The weaker the association, the less informative the value on the independent variable is when we make predictions about the value on the dependent variable. And of course, if you have zero correlation, no correlation between the independent and dependent variable, what kind of regression line will we get? It goes like that. What is the intercept here? It's the same as the mean on the dependent variable. If a person has this value on the independent, what will we predict that he or she has on the dependent variable? The mean. And there, the mean. And there, the mean. We will always predict that the individual on the dependent variable has a value that equals the mean. We completely ignore what value he or she has on the independent variable. We ignore it completely. We predict the mean all the time. Does that sound sensible? Does it sound sensible to ignore the value on the independent variable? Yes. Because if there is no association, it doesn't tell us anything about what value this person might have on the dependent variable. it gives us no information whatsoever, and therefore we ignore it. And instead we always predict that the person will have a value that equals the mean. Why do we predict the mean? Why not always predict that individuals have a value that is, I don't know, 3 standard deviations above the mean? Why do we always predict the mean? Wouldn't it be better to predict 3 standard deviations above the mean? No, the mean is probably the best prediction. Why? What value do people tend to have on a certain variable? Most of them, a variable that is normally distributed. Most have a value that is close to the mean. So we make the best guess. If you're going to guess what value a certain person has on a certain variable, you guess the mean. That's the best you can do with no other information. And in this case, even if we know the value on the independent is no information, it's not useful. And therefore we guess the mean. Isn't that nice? Galton's philosophical thoughts comes into the calculation of the regression line here. If we have complete regression towards the mean, well, then we always predict the mean. And we always make an adjustment of our... As long as the correlation here is not -1 or +1, we always make a certain adjustment towards the mean. The weaker the association is, the more adjustment we make towards the mean. I'm going to make a point about the similarity between regression and ANOVA. And those are, as I said a few times, they are actually the same analysis, the same general linear model. The other day we went through analysis of variance, and we had a look at many sum of squares. And the same could be done here, calculating sum of squares. In SPSS, when you conduct the regression analysis, you get the ANOVA table also, with sum of squares and a F ratio and a p-value to that. Okay, so let's have a look here. We have our data. And we can calculate total sum of squares. And regression, something I call regression sum of squares and residual sum of squares. So total sum of squares, how do we calculate that? It gives a measure of the total variation in the dependent variable in our data set. So it would be these green lines here. So for every individual value, for every actual value, we take the value minus the mean on the dependent variable, square that, and take the sum over all individuals. Sum of square differences between the observed values and the mean on the dependent variable. Total sum of squares. How much nuances there are in the dependent variable in this sample. Regression sum of squares. It's pretty much the same as between group sum of squares in a one-way ANOVA. And how did we calculate that? Between, I can't. Do you remember that? Between group sum of squares. We replaced each value, each actual value on the dependent variable with the sample mean. And then had a look how after the replacement the values deviated from the mean. Now we do pretty much the same. But now we don't have sample means anymore. But what are the sample means similar to in a regression analysis? It's the predicted values. When you conduct a one-way ANOVA, you, so to speak, for every individual, you predict that their value on the dependent variable is the same as the mean in the group they belong to. So the predicted value is the mean in the group. Now we don't have groups, but we have a regression line. And those are the lines, the values on the regression line are our predicted values. So if we replace each value with predicted value for that level of the independent variable, and then we take minus the mean, square that, and take the sum over all individuals. So this person has that value on the dependent variable, but according to the regression line, that person is predicted to have that value, and we take that value, predicted value minus the mean, and square that. Of course, in this simplified example, we have only one individual for each level of the independent variable, but usually you have several. So we might have several individuals with 5 therapy occasions. But we would, for all of those, predict that they have that value on the dependent variable. So we would replace every value, observed value, with predicted value, and then calculate the sum of squares. And we call that regression sum of squares. It gives an indication of how much of the nuances in the dependent variable are left when we replace actual values with our predicted values. How much of the information is retained in our regression model? How much of the information about individuals' values on the dependent variable is covered by our regression model? And how much is lost? If we replace each observed value on the dependent variable with our predicted values, how much is lost? Well, it's the within group sum of squares from one sample, one-way ANOVA. It's the differences between the actual values, the observed values, and the predicted values. We take those differences, square them, and take the sum over all individuals. That is the amount of information about individual values on the dependent variable that is lost when we replace the actual data with our regression model. That is the information that is not covered by our statistical model. And the sum of regression sum of squares and residual sum of squares equals total sum of squares. In the same way as between group sum of squares and within group sum of squares, total sum of squares in a one-way ANOVA. If you have a look at our example here, we have 5 individuals. We have how much therapy they receive. We have their life satisfaction. If we take each individual value minus the mean, which is 3.4 in this case, and square it, and do that for all individuals, and take the sum here, 21.2. Total sum of squares. Predicted life satisfaction, according to our formula that we calculated before. That is the level of life satisfaction individuals are predicted to have based on the amount of therapy, according to our regression line. We can calculate, I jump here, the regression sum of squares. In each row, we take the predicted value minus the mean, 3.4, and square that, and do that in each row. Okay, we see here this person is predicted to have exactly the mean, so it becomes 0 here. And then we take the sum here, 16.9. How much is lost? In each row, we take the difference between observed life satisfaction and predicted life satisfaction, square that, and take the sum here, 4.3. So here is how much variation we have in life satisfaction. Here is how much is explained by our regression model based on how much therapy they get, and here is how much is lost. We can calculate the F ratio. So we take regression sum of squares divided by regression degrees of freedom. And regression degrees of freedom is the same as number of predictors. So in this case, 1. If we take sum of squares divided by degrees of freedom, what do we get? What do we get? What is it called? Sum of squares divided by degrees of freedom. An ANOVA table is usually called the mean square. Mean square is the same thing as variance. So that's regression variance, so to speak. Between groups variance. The equivalent for that from one-way ANOVA. We take residual sum of squares, 4.3, divided by residual degrees of freedom. And residual degrees of freedom is number of individuals minus number of predictors minus 1. So in this simple example, it's 3. So we have regression mean squares, residual mean squares, and we make a ratio of those 11.8. What do we do with this F ratio? What do we test with it? If we take our regression sum of squares here, 16.9, and divide it with total sum of squares, 21.2, we get a percentage. How big portion of the variance in the dependent variable can be explained by our regression model? Amount of explained variance. That's what we get. It's a percentage. What do the null hypotheses say in regression analysis? We're still at simple regression here. So what does the null hypothesis say? In the population that the sample represents, there is no association between the independent and dependent variable. In this case, in the population, there is no association between amount of therapy and level of life satisfaction. If that is true, that there in the population there is no association, how much of the variance in life satisfaction can be explained by amount of therapy? How much? Nothing. 0%. That's what the null hypothesis says. In the population, the independent variable can explain 0% of the variance in the dependent variable. So what we can do with this F ratio is to do a significance test. Does the amount of explained variance in our sample differ significantly from 0? That's what we're going to use it to. If we get a significant result, we assume that the amount of explained variance in the population is not 0. It's more than 0. So the independent variable can explain at least some of the variance in the dependent variable in the population the sample is representing. So we get the F ratio in this case 12. Can you guess if the population amount of explained variance, if the amount of explained variance in the population is 0, what do we expect this F ratio to be? What is the baseline, so to speak? What was the baseline F ratio in one-way ANOVA? If the null hypothesis was correct, we expected the F ratio to be more or less 1. It's the same here. If we have 0% explained variance in the population, we expect the F ratio to be close to 1. Okay. So in this case, it became much more than 1. It became 12. It became 12 times as large as we expect. We could compare that F ratio, our calculated observed F ratio. We could, for instance, compare it with a critical F ratio taken from a F distribution, because of course there are those also. So if you have a look at F distribution, we take out the critical value. on the level of 0.05, our significance level, with 1 and 3 degrees of freedom. 1 and 3 degrees of freedom. In that F table, we would find the value of 10.1. How do we interpret this value? 10.1. And F values, because they are ratios, they can only be positive. There is no negative F ratios. How do we interpret this? If we have a population where we have 0% explained variance, in this case, if in the population the sample is representing, amount of therapy explains 0% of the variance in life satisfaction. If that is the case, what do we expect? We expect the F ratio in a sample of this size, in all samples actually, to be more or less 1. Okay, but in samples of this size, the calculated F ratio with the probability of 95% will be maximally 10.1. So if the null hypothesis is correct, we have 0% explained variance in the population. F ratio in a sample of this size will, with 95% probability, be maximally 10.1. What F ratio did we get? 11.8. What is the probability of this happening if it's 0% explained variance in the population? It's less than 5%. So what do we assume? The amount of explained variance in the population it's not 0. There is at least some degree of explained variance. In the population, amount of therapy can explain more than 0% of the variance in life satisfaction, which is the same thing as saying there is an association in the population. The amount of explained variance you get by dividing these regression sum of squares by total sum of squares. Does that sound kind of familiar? What did we do in ANOVA? To effect size, how did we calculate effect size? The simple way, so to speak. Between groups. Sum of squares. Between group sum of squares divided by total sum of squares. It's called eta squared. This is the same. Explained sum of squares divided by total sum of squares. But now it's called R2 instead. R squared. R raised to 2. But it's the same thing. Okay, so let's have a look here. I want to make a point. And I'm not making it very nicely from a mathematical point of view, but okay. So I have a data set here. It doesn't matter what data it is. I just have a few items here. So I make a regression analysis here. I predict values on item 31 from values on item 1. The correlation between those two items is 0.04. Sum of squares total variation in item 31, 687. If I do this regression analysis, I get regression sum of squares 0.96. If I take the ratio here, I divide 0.96 by 687, I get this value. It means that I have 0.1% explained variance. 0.1% of the variance in item 31 can be explained by values in item 1. So I do that a few times. So I had to look one up where I have at least some degree. So here, item 18 and 17, the correlation between them is 0.76. total sum of squares, the regression sum of squares, the ratio of those, 58% explained variance. 58% of the variance in item 17 can be explained by the values on item 18. And now we have a look. You see these column correlations and these column explained variance when we do a regression analysis. Is there some kind of relation between those two? Yes, there's a very strong relation between those two. If we take the correlation and square it, if we take those values, square them, we get those values. So if you have two variables and you have a correlation, if you square that correlation, you get how much of the variance in one of the variables can be explained by the values on the other variable. Amount of explained variance. And of course, because you square, it doesn't matter if it's a positive or negative correlation. So correlation squared is the same thing as explained variance. Here we have SPSS output. So we predict life satisfaction from amount of therapy. And we get a few values. We get something that's called multiple correlation. It's a correlation between observed and predicted values on the dependent variable. So if I go back a little bit here. So here we have observed values on life satisfaction, and here we have predicted values on life satisfaction. So if we take the correlation between those two, we get the multiple correlation. In this case, 0.89. In simple regression, when we only have one predictor, one independent variable, that is exactly the same as the correlation between the two variables. Okay, but a more general rule is that it's the correlation between observed and predicted values. If we square that, we get the next value, or square. How much of the variance in the dependent variable can be explained by the independent variables? In this case, it's only one, so by therapy. 80% of the variance in life satisfaction can be explained by how much therapy you receive. If we say that the only thing that matters for your life satisfaction is how much therapy you get, then that statement will be 80% true and 20% false. God, that sounded crazy statement. But we would, so to speak, cover 80% of the actual variance in life satisfaction by saying that. We have seen how we get these values: regression, residual, and total sum of squares. And we already calculated this F ratio, 11.8. Now we actually get the p-value also, 0.04. How do we interpret that? What does it tell us? What conclusion do we draw from that p-value of 0.04? If the population R-square is 0, so it's 0% explained variance in the population, what is the probability of, in a sample like this, of this size, getting an R-square that deviates this much from 0? Actually this much or more. How high is that probability? 4%. So what conclusion do we draw? In the population R-square is not 0. It's higher than 0. So in the population, you can explain at least some of the variance in life satisfaction from amount of therapy. Doesn't this sound crazy? We have a huge amount of explained variance in our sample, 80%. And it becomes significant, but still only with a p-value of 0.04. Right? You will never get explained variance this high when you do your own research. I'm happy if I get 20%. So how come that the p-value is this high, although we have this huge amount of explained variance? Why? Why is the power very low? Yeah, it's extremely small sample with 5 individuals. That's why. With a normally sized sample, this value, we would only see zeros here. But with this example, with only 5 individuals. Okay, if you have a look, we've seen those already. Our intercept, it's called constant here. Predicted life satisfaction if you don't receive any therapy, 0.5. 1.3, when therapy goes up with 1, life satisfaction is expected to increase by 1.3 on the scale from 1 to 7. Standard error, we already calculated that. What did that stand for now again? The standard error of 0.38 here for the regression coefficient. What does it stand for? What is it an estimation of? The standard error. I noticed I talk about nothing else as much as I talk about standard error. It's an estimation of how much the regression coefficients calculated in samples of this size, on average, deviate from the regression coefficient in the population. That's what it stands for. What do we do with our regression coefficient, 1.3 here, and its standard error, 0.38? What do we do with them? What is done with them in this table? How do we get t-values in general? You take something, and what do you do with it? You have a parameter value. It could be a mean. It could be a regression coefficient. It could be something else. What do you do with it? You divide it by standard error. So we take 1.3 divided by the standard error. We get our t-value over here. And it's significant. In simple regression, that p-value and that p-value will be exactly the same. We have a beta coefficient here, 0.9. What does it tell us? If amount of therapy increase by 1 standard deviation, what happens then? What do we predict will happen then? If amount of therapy increase by 1 standard deviation, life satisfaction is predicted to increase by 0.9 standard deviations. In simple regression, that value will be exactly the same as multiple correlation up there, which is the same as ordinary correlation between the two variables. Yeah, maybe I make this point also. R square is exactly the same as the ratio between regression sum of squares and total sum of squares. Those are the same thing. Some assumptions and recommendations. As I said, we're predicting change, increase, decrease, so we have to be able to talk about increase, decrease. So the variables must be at least on ordinal scale, actually on interval scale, depending on how hard-headed you are. I'm not so hard-headed. Go along, do a linear regression. Or do both and compare. They usually indicate the same. If you have, there are special kinds of regression for ordinal data also. So. Okay, but not nominal data. You can not have nominal data. Not as the dependent variable. As the independent variables, one of them, you can have nominal data, but only one kind, namely dichotomous. So dichotomous or continuous predictors. Continuous dependent variable. You must have data from at least 2 more individuals than you have predictors, because otherwise you don't have any residual degrees of freedom, and you will have a 0 in the denominator and you can't do the calculations. But of course, we want much more persons than that. I don't know, I caught these recommendations from somewhere. I guess there is some mathematics in the bottom, they just sound a bit funny. People come up with. Somebody said that number of individuals should be at least 50 plus 8 times number of predictors. Number of independent variables. Somebody else said, number of individuals should be at least 104. How do you come up 104? 103 is not enough. Must be 104 plus number of predictors. But of course, the general rule is the more the better. The more data you have, the better it is. Assumption, observed values independent of each other. And I mean, I say this a few times, might be a bit confusing, but the value of one individual, for instance, on the dependent variable, shouldn't be affected by some other individual's value on the dependent variable. For instance, if our dependent variable is life satisfaction and we have a few married couples in our data set, of course, one of the spouse's value on life satisfaction might have a relation with the other spouse value on life satisfaction. And that's not good for the analysis. It assumes that the values are independent of each other. We have assumptions here about the variables, that in the population, the variance on the dependent variable is the same for all levels of the independent variable. And also that the values on the independent variable are normally distributed for all levels of the independent variable. So what we want is it to look something like this. So for all levels of the independent variable, the variance on the dependent variable is more or less the same. We don't want it to look like this, so that the variance for some levels is much larger than for some other levels. It will be more difficult to fit the regression line to these data. We can, to a lower degree, trust the results we get. And we also want the values of the dependent variable to be more or less normally distributed for every level of the independent variable here. Of course, with small samples, it will never look very nice, but this is an assumption about how it looks in the population. We'll do some diagnostics about this when we run SPSs. Not formal significance test of this, but we'll have a look at it. Outliers can affect data to a high degree, can affect the calculation of the coefficients to a high degree. They have high influence, as it's called, which means that you get the regression coefficient if this person is in the data set, but something completely different if this person is not in the data set. Does that sound good? Assuring? No, because of course we want to come up with a regression model that gives a good description of how the association between the variables look like. And if it's completely different with one person in the sample compared with without, we can't be sure which is the true statistical model here. So we don't want to have outliers like that. So we can diagnose for that also. We can calculate something called DF beta. It's an influence statistics. How every individual with their values influence the calculated parameters, the calculated coefficients. And we don't want to see any extreme values on that. We want the result would be more or less the same if we took this person out or had them in the analysis. So now we come to multiple regression. So we still have one dependent variable, one continuous dependent variable. And we're going to predict what value people have on this dependent variable based on what values they have on two or more independent variables. So now we have several predictors. And again, the predictors can be either continuous or dichotomous. So we might have data like this, for instance. People receive differing amounts of therapy and differing amounts of medicine, and we measure their life satisfaction. Okay, so we get the formula that looks like this. So we say like this. A person's predicted value on the dependent variable equals an intercept plus his or her value on the first independent variable multiplied by a coefficient plus his or her value on another independent variable multiplied by a coefficient, and so on. So we get one intercept and one regression coefficient for each independent variable. What does the intercept stand for? The predicted value on the dependent variable if all predictors are 0. If we put in 0 for every x here, only thing we have left is the intercept. Predicted value on the dependent variable if all predictors are 0. And the regression coefficients, what do they stand for? So here, for instance, we have a regression coefficient for predictor 1. So what does it stand for? It stands for how much does the value on the dependent variable change if that predictor increases by 1 and all other predictors are kept constant. If everything else is equal, what happens with the dependent variable, the value on the dependent variable, if the value on this independent variable increases by 1? That's what it stands for. So it stands for the unique effect, the unique association between that independent variable and the dependent variable. And again, the intercept and the regression coefficients are calculated, so we minimize the sum of squared differences between observed and predicted values on the dependent variable. One thing we might get trouble with in multiple regression is something called collinearity. Because we're going to calculate the unique association between each independent variable and the dependent. Therefore, we want there to be some kind of unique association. And that might not be the case. There might not be any unique association between an independent and a dependent variable. Because the information in one independent variable might already be explained by the other independent variables. So it doesn't contribute any unique information into the regression model. Whatever it can explain can already be explained by the other independent variables. That's collinearity. And of course, this you can have differing degrees of collinearity. High degree of collinearity means that the unique information that a certain independent variable contributes is very low. And what this might lead to is that it will be difficult to calculate the regression coefficients. Because it assumes that there is some kind of unique association between the independent and the dependent variables. And if there's not, of course it does its best, but it will be difficult to calculate. And we might get very strange results. For instance, there might be we might get very strange results. Small changes in the data might lead to big differences in the results. So the computation becomes difficult to carry out. So we should check for this, for collinearity. And in SPSS, you can tick a couple of boxes. Now it's enough with one. And we get something called the tolerance and something called the variance inflation factor. And those are measures of the degree of collinearity. Okay? And you get one for each independent variable, because they can differ. Tolerance. So let's say we have 3 predictors. I only have 2 here in my example, but let's say we predict life satisfaction from therapy, medicine, and age. Okay, then we get a tolerance value for medicine. What does it stand for? Well, what the program does, it predicts the values on medicine from the 2 other predictors, from therapy and age. So it conducts a regression analysis. It predicts values on medicine from therapy and age. And it calculates a R-square. And the R-square stands for how much of the variance in medicine can be explained by therapy and age. Okay? How do we want that R-square to be? Low. Because we want medicine to contribute unique information. So we want the R-square to be low. Tolerance is 1 minus that R-square value. So it stands for how much of the information in the predictor cannot be explained by the other predictors. How do we want that value to be? High. It's simple to remember. We like tolerance, so we want it to be high. And it can maximally be 1, means that the predictor is completely independent of the other predictors. And there's a few rule of thumbs. I read this somewhere. It says it should be at least 0.4. I guess those rule of thumbs, you take them with some salt. You can find several rule of thumbs, but it should not be too low, the tolerance value, because that indicates it might be computational problems for the analysis. The variance inflation factor, we also get this in SPSS, is 1 divided by tolerance. And I think it's so funny. What are we using this for? We are using these measures in order to measure the degree of uniqueness. And we have 2 measures that contribute no uniqueness, because from one you can calculate the other. If you know the tolerance value, you can calculate the VIF value, because it's 1 divided by tolerance and the opposite. So it's enough to have a look at one of them. They don't contribute unique information. But in this case, of course, we would like this to be low. And it can minimally be 1. And if we use the same rule of thumb, if tolerance, we want it higher than 0.4, it means that we want this VIF to be lower than 2.5. But it's enough to have a look at one of them. For instance, the tolerance value. Let's say we have 3 predictors, medicine, therapy, and age. And the tolerance for medicine is 0.4. It means that 60% of the variance in medicine can be explained by therapy and age. According to this rule of thumb, you shouldn't get more than 60% explained variance. Not more than 60% of the variance in one independent variable should be explainable from the other independent variables. We could again do this in the form of calculating sum of squares and so on. So amount of therapy, amount of medicine, degree of life satisfaction, total sum of squares, variation in life satisfaction. We have predicted values, predicted life satisfaction according to this formula. We'll have a closer look at that soon. Predicted life satisfaction is 0.9 plus 1.1 multiplied by amount of therapy minus 0.5 multiplied by amount of medicine. So that's what we have there. Predicted values. Regression sum of squares. In each line, we take the predicted life satisfaction minus the mean, which is 3.4, square that difference, and take the sum here. 17.53. Residual sum of squares, we take the difference between predicted and observed values. So the difference between those and those values, square them, and the sum here. 3.7. So 21.2 total variation in life satisfaction. 17.5, the amount that can be explained by our regression model with the predictors therapy and medicine. And 3.7, the amount that cannot be explained by our regression model. Of course, these values don't seem very, you don't get these high regression sum of squares normally when you do real analysis. We can calculate the F ratio, take the regression sum of squares, 17.5 divided by regression degrees of freedom, 2, because we have 2 predictors. We do the same for the residual sum of squares divided by residual degrees of freedom, also 2, and we get the value 4.8. What are we testing with this F ratio? What are we testing? Why are we calculating a F ratio? We want to test if we can assume a certain thing about the population that the sample is representing. What are we testing? We are testing whether we can assume that life satisfaction, variation in life satisfaction, can be explained by variation in therapy and variation in medicine in the population the sample is representing. What is the null hypothesis? We could express it in the form using explained variance. The null hypothesis is that the amount of explained variance in the population is 0. The zero hypothesis is, the null hypothesis is that R square in the population is 0. If the R square in the population actually is 0, what do we expect this F ratio to become? More or less. More or less 1. If the amount of explained variance in the population actually is 0, we expect this to be more or less 1. How high is the probability of getting an F ratio that is this high if the amount of explained variance in the population is 0? How high is that probability? You can't say it exactly, but by comparing with that value, you can say that that probability is the probability of getting our data. If it's 0% explained variance in the population, that probability is it's more than 5%. Because this value here says that if it's 0% explained variance in the population, the probability is 95% to get the F ratio that is less than 90. And in this case, our F ratio is less than 90. So the probability of getting our data, if it's 0% explained variance in the population, is more than 5%. So what conclusion do we draw from that? The amount of explained variance in population could be 0. We cannot with enough confidence reject that it would be 0. So it could be 0. If we have a look at the output here. Doesn't that sound strange? We have huge amount of explained variance here. 83%. But we still cannot reject that it would be 0% in the population. Well, it's because we have extremely low power here. 5 individuals. So our p-value here is 0.70. We can't reject the null hypothesis that the R² is 0 in the population. Okay, I'm going to present a few other values here. Adjusted R². What is that? So in this case, we have R², 83% explained variance. 83% of the variance in life satisfaction can be explained by amount of therapy and amount of medicine. When we use this intercept and these regression coefficients. How has these coefficients parameter values been estimated? They've been estimated to give as much explained variance as is possible in this sample. So everything is optimized to give as much explained variance as is possible in this sample. Let's imagine we draw some other sample from the same population. And then we use the same intercept and the same regression coefficients to make predictions in this other sample. Will we get 83% explained variance in that sample? Can we expect to get 83% explained variance in another sample drawn from the same population? No, because everything is optimized for this sample. Therefore, we can expect to get less explained variance in another sample. How much explained variance can we expect to get in another sample? Actually, I never heard somebody else saying this, and I haven't written it, but I still say it. This is how much explained variance we can expect to get in another sample. If we use the same model with the same intercept and the same regression coefficients to do predictions in another sample. On average, in other samples, we drawn from the same population will get 65% explained variance. It's an estimation of that. Is that good to know? Is that good information? Yeah, of course, because regression models are often developed and used in order to make predictions. We have some data for students, for instance, and we predict how is their outcome during their education. And we predict it from a few variables. And we make a regression model. And we want to make predictions about the future. So we get new students, we measure the predictors, and then we predict their outcome. How will they succeed with their education? But now you should know you cannot expect your regression model to give as good predictions among new students. Because your regression model has been optimized to function optimally in your former sample. It will not work as well in other samples. You cannot expect to get as good predictions in other samples. You get the adjusted R² from R² with this formula. N is the sample size, and P is number of predictors. So if we see the adjusted R² will always be lower than the R². Or in some cases, they're pretty much the same, but it never gets higher than the R². And when is there a big difference between R² and adjusted R²? Well, we see here the more individuals we have, the larger the sample size we have, and the fewer predictors we are using, the smaller is the difference between R square and adjusted R square. Because R square is biased, and the level of it being biased is affected by sample size and number of predictors. The smaller our sample is, and the more predictors we are using, the more biased the R square is. And the more biased it is, the bigger the difference between R square and adjusted R square. If we have a large sample and use a simple regression model with a few predictors, then the difference between adjusted R square and R square usually is not very big. We saw that our F ratio is not significant, means that although we have 83% explained variance in our sample, it could still be 0% explained variance in the population. It does not differ significantly from 0. This is also taken as an omnibus test. If the ANOVA was non-significant in one-way ANOVA, how did we interpret it? If the ANOVA was non-significant, we retained the null hypothesis. And what did the null hypothesis say? It said that in one-way ANOVA, all populations have the same mean on the dependent variable. So it's an omnibus test. And if it was significant, what conclusion did we draw in one-way ANOVA? At least two of the populations differ. At least one of the differences is differs from 0. Here, if this is non-significant, we draw the conclusion all regression coefficients for all predictors might be 0 in the population. They might all be 0. If this one would be significant, we would draw the conclusion that not all regression coefficients are 0. At least one of the regression coefficients for one of the predictors differs from 0 in the population that the sample is representing. And then we would go further and have a look. What predictors have coefficients that differ from 0? So a bit similar. ANOVA and then post hoc test here. So here we have our parameter values. Our intercept, 0.9. What does that mean? If you don't get any medication and no therapy, your life satisfaction is predicted to be 0.9. Okay? That's what the intercept stands for. We have a coefficient for therapy here. Let's ignore that they're not significant for the moment. We have a coefficient for therapy here, 1.06. How do we interpret that? If we keep medicine constant, an increase in therapy by 1 is predicted to be associated with an increase in life satisfaction by 1.06 points on the scale from 1 to 7. If therapy is kept constant, an increase in medicine by 1 is predicted to be associated with a decrease in life satisfaction with 0.5 on the scale from 1 to 7. So the unique association between each predictor and the outcome variable. Beta coefficients, 0.7 for therapy. How do we interpret that? If therapy increased by 1 standard deviation, we anticipate life satisfaction to increase with 0.7 standard deviations, given that medicine is kept constant. Exactly. And the same for medicine. If we keep therapy constant, an increase in medicine by 1 standard deviation is associated with a decrease in life satisfaction by 0.24 standard deviations. What is good about beta coefficients compared with the non-standardized regression coefficients? We can compare them. What does this indicate? Yes, therapy has a stronger unique association with life satisfaction than medicine. Because it has a beta coefficient that differs more from 0.
So we should compare the
Absolute values, yes. Negative or positive doesn't matter. It's how much it deviates from 0. T-values, how do we get those? How do we generally get t-values? If I want to get a t-value for my bicycle, what do I do with my bicycle? I divide it by its standard error. So you take the coefficients here, divide them by their standard error, and you get the t-values. And then we go further to a p-value. If there is no unique association between therapy and life satisfaction, if there is no association between therapy and life satisfaction in the population, given that you keep medicine constant, what is the probability of getting a regression coefficient that differs this much from 0? How high is that probability? 22%. So it might happen. We can't with enough confidence reject the null hypothesis. And the same for medicine here. We can't, without enough confidence, reject the null hypothesis. For both of them, the regression coefficient in the population could be 0. Yes, and that was indicated also by the ANOVA table here. What kind of problems can you have with when you conduct multiple regression? Collinearity. Do we seem to have any grave problems with collinearity here? No. We have tolerance value 0.52, and if you only have 2 predictors, they will always be the same. That might not be the case if you have three or more, but because this is based on a simple regression. 52% of the variance in therapy cannot be explained by medicine. 52% of the variance in medicine cannot be explained by therapy. And according to a rule of thumb here, if it's above 0.4, it's okay. So if we stick to that rule of thumb, then it's okay. We see the correlation here is quite strong between therapy and medicine, minus 0.7. But it still passes that rule of thumb of tolerance. So actually, if we take 1 minus the square of that correlation, we get the tolerance value here. Now, of course, you wonder, right? How does it calculate those individual coefficients? How do you calculate the unique association between a certain predictor and the outcome variable, controlling for the other predictors? I don't know if you're interested, but I became interested, so I thought I'll have to have a look at this. And this is how you do it. So we have therapy, medication, life satisfaction. And we use life satisfaction as the outcome and the 2 others as predictors. So let's do the following. We use medication as a predictor. And we predict therapy from medication. A simple regression. And we get a formula like this. Predicted therapy is 4.4 minus 0.1 times medication. So in that case, we can predict for each individual how much therapy are they predicted to have according to the amount of medication they're eating. So we can calculate the predicted therapy, and we have the actual therapy, and then we take the difference between actual therapy and predicted therapy. Residual for that analysis. Here are those residuals. The residual when you predict amount of therapy from amount of medicine. What does those values stand for? It stands for the amount of therapy that people receive that cannot be explained by how much medicine they eat. Right? Residuals cannot be explained. Then we do the same for life satisfaction here. We predict life satisfaction from amount of therapy. From amount of medicine. We get that predicted life satisfaction is 5.5 minus 1.5 multiplied by amount of medicine. So we can predict for each individual, and then we take their predicted life satisfaction minus, actually the other way. We take their observed life satisfaction minus the predicted life satisfaction. We say the residuals here. What does those values stand for? They stand for the level of life satisfaction that cannot be explained by amount of medicine. What do we do now? Now we predict those values, residual life satisfaction, from those values, residual therapy. And we get this formula. Residual life satisfaction is 1.059 multiplied by residual therapy. We don't get an intercept. Why don't we get an intercept? Because it's 0 is the mean for those, both those. And how do you say? Behold, that's our coefficient here. So it's the amount of life satisfaction that cannot be explained by amount of medicine, predicted from the amount of therapy that cannot be explained by amount of medicine. That's how you get these unique coefficients. It's wonderful. And we could do the opposite here. We use therapy as predictor. We predict medicine and save the residuals. We predict life satisfaction, save the residuals. Actually, we already done that before. And then we predict residual life satisfaction from residual medicine. And we get this. Residual life satisfaction is minus 0.481 multiplied by residual medicine. It's beautiful. So the unique effect, unique coefficients, is the same when you predict residuals from residuals. That's how you control for the other predictors. You calculate residuals, and then you use them in regression analysis. I don't know if you get excited. I got very excited for a few hours there. It makes sense. Okay, selection methods. You can select your predictors in different ways. So the ordinary way here is called enter. You tell the program, you tell SPSS, here's the predictors. Use all of them. And it puts all of them into the model and calculates the unique association for each predictor and the dependent variable. We decide. These are the predictors that you are going to put into the model. Hierarchical model, then we put them in, we can put the predictors in differing orders. We tell the program, first you put in these predictors. And then in the next step you put in these predictors. The end result will be exactly the same as if you put everything in at the same time. So the coefficients in the end will be exactly the same. But what you get here, for instance, can get is R square change. How much does the explained variance increase when you put in a new variable and already controlling for predictors that's been put into the model at an earlier step? That's, for instance, popular in sociological research, because you're always supposed to control for social background. You always control for sex and social background. And then you have a look at the thing you're really interested in. So you put in sex and social background as predictors at step 1, and then you put in what you're interested in. And then you can see above the effects of sex and social background, how much more of the dependent variable is predicted when we put this new predictor into the model. Does the model improve significantly when we put in this new variable? Okay, we can also use these forward and backward, and a combination of them. That's called stepwise. The stepwise functions like this. You tell the program, here is a bunch of predictors to choose among. I don't know which should be in the model. I leave it to you to decide. And the program calculates, does any of these predictors improve the model significantly if we take it in as a predictor? So it ranks the predictors. And it takes the best predictor and puts it into the regression model as a predictor, if it's significant. And then it has to look at the other ones. Given that this best predictor is already in the model, can the inclusion of any other predictor make the model significantly better at predicting variance in the dependent variable? If somebody else still has a significant effect controlling for the first predictor, it's put into the model. It can also throw out predictors if they stop being significant. So it works both ways. And the end result is that the program tells us, here are the predictors that significantly improve the model's predictive capacity. So they are included in the model, and the rest, they are excluded. We don't have to say these are the strongest and this is weakest. We say here is a number of predictors. Have a look at them. Take the best ones, the strongest one, and take them into the model as long as they significantly improve the model's predictive capacity, which means they increase the R square significantly if they're taken into the model compared with if they're not. So the program can do this for us. We don't have to rank them. The program does that. Okay, so let's have a look. Here is a hierarchical model. So in the first step, I put in therapy as a predictor, and we have 79.7% explained variance. R square change. In the first step, it's compared with 0. So R square increases from 0 to 79.7%. And we get the F value, F ratio for the change, and we see it's significant. So a model with therapy as a predictor is significantly better at predicting life satisfaction compared with a model with no predictors. Step 2. We keep therapy and we add medicine. And the R square increases from 79.7 to 82.7%. So it's an increase by 3%. But this increase is not significant. So if therapy is already in the model, it doesn't improve significantly by adding medicine as a predictor. We could, of course, go in the other direction. we put in medicine at the first step. R square increases from 0 to 55.5%. But that effect increase is not significant. So a model with medicine as predictor is not significantly better than a model with no predictors. If we then in the next step add therapy, it increases to 82.7%, and that of course is exactly the same as there. It increases by 27.5%, but that increase is not significant. So of course here we might get the picture. None of them is significant, but that's because therapy is actually significant, but it's not significantly improving the model if medicine is already in the model as a predictor. If we do a stepwise, what do you think the result will be? We have only therapy. So therapy is included, and we get exactly the same values as we did before here. And excluded. Medicine is not included in the model. So if you want to illustrate this somehow, you have it like this. I never talked to these slides before, but imagine the white circle here. It's a variance in life satisfaction. The total variance in the life satisfaction. From the values we saw there, 27.5% of that variance can be explained by only therapy. 3% of that variance can be explained only by medicine. 52.2% can be explained by both therapy and medicine. So if we add those 27, I took them from the hierarchical output. So if we add those two, 27.5 and 52.2, we get 79.7%. That's how much of the variance in life satisfaction that can be explained by therapy. The same here for medicine, 3% plus 52.2%. 55.2% can be explained by medicine. And in the end, if we add all those, we get 82.7%. 82.7% can be explained by therapy and medicine together. The 79.7% explained variance for therapy, it's the same as the correlation between life satisfaction and therapy squared. 55.2% explained variance. 55.2% of the variance in life satisfaction can be explained by medicine, and that's the same as the correlation between those two variables squared. I don't know if you have come across partial correlation, semi-partial correlation. Well, it's related to this. You could calculate them like this. Semi-partial correlation, you take the root, in this case semi-partial correlation for the association between therapy and life sat. You take the root, square root of this number. 0.524. Partial correlation, slightly differently. Okay, I say no more about that. If you become interested somehow, someday you'll have these slides. Partial correlation and beta coefficient, although I'm not sure they have to be exactly the same, but they're very closely related. Okay, we come to a few special cases of regression. So far we talked about linear regression, but not all associations are linear. Imagine we have data like this, for instance. Medication and life satisfaction. And we apply a regression line according to all rules. That's what I've done. And here it is. And we get 0.3% explained variance. You see, the adjusted is even negative. It's worse. It's worse than randomness. But is there no relation between medication and life satisfaction? There is. Clearly there is, but it's a non-linear association. It's a curvilinear association. So what we want to do is to change this straight regression line to a curve instead. And how do you do that? How do you go from a line to a curve? This is the general formula for a curve. So we say a predicted value on the dependent variable is an intercept plus a coefficient multiplied by the value on the independent variable plus another coefficient multiplied by the square of the value on the independent variable. Then you get a curve instead of a straight line. So what we do is that we take our independent variable and we square the values. And then we put in both our original value and the squared values. Put them both into the model as predictors. And we get the intercept and two regression coefficients. And we're mainly interested in this regression coefficient and to see if it's significant. If it's significant, it shows that there is a significant curvilinear association between the independent and the dependent variable. So that's how we fit a curve to the data. So let's have an example here. So we have amount of medicine, level of life satisfaction. So I take those values, we take those values, medication, and we square them. And that's what we get. But I try a bit differently here. So I set or standardize the medication values. So we take those values and we standardize them. And we get these values. So this person, for instance, with a value 1.17, what do we know about this person? How much medication is he or she receiving? 1.17 standard deviations over mean, more than the average. Okay, of course the values don't become so realistic here with so few values, but okay. So that's the standardized values. And now we take those and square them, and we get these values. So we try two different combinations. We predict life satisfaction from medication and the square of medication. That's one model. In the other model, we again predict life satisfaction from standardized medication and the square of standardized medication. And we'll have a look. Okay, so here we have the non-standardized predictors. And here we have the standardized predictors. How much of the variance in life satisfaction can be explained by our model, by our curvilinear model? 80%. I guess it's a bit scary. It became exactly the same as before, but it's team data, so I guess that was by chance. 80%, and it's exactly the same in both cases here. So that's not affected by the standardization. Can we assume that there is a curvilinear association between medication and life satisfaction? Yes, why? From what value do we draw that conclusion? The p-value for the squared term here, it's significant, and it's exactly as significant here. So the two models indicate the same thing. However, does any one of them have an advantage compared with the other one? If I say the one with standardized values have an advantage compared with the one with unstandardized, what advantage does it have? Collinearity. We have very low tolerance here. While here we have perfect tolerance, no collinearity. Okay, this is not a problem, really, if you just have this. But imagine you put in a third predictor. Then the computation will be tricky for this first model, because we have such a high degree of collinearity. This model would be more robust, because we have no problems with collinearity. How come? Why do we get collinearity in the first model but not in the second? Well, let's go back here. You see medication here, and medication squared. Is there any association between those two variables? Any linear association between those variables? Between medication and the square of medication? Yeah, it's exponential. It's very strong positive association. How about this standardized medication and the square of that? Is there any linear association between those two? No. The squared values are lowest in the middle here for those with the mean values, and highest for those who deviate from the mean. So there's a curve linear association, but no linear. And the tolerance, the collinearity, is based on linear association between the predictors. So what we, so to speak, do, and this is what happens if you have a variable with only positive values, and you square those values, then of course the higher your value on the original variable, the higher your squared value is. And you tend to have a strong positive association, and you risk to get collinearity. While if you have a variable with both positive and negative values, it's those that deviate more from zero that becomes high when they're squared. And you so to speak destroy the linear association, and you get lower degree of collinearity in your analysis, and the analysis become more robust. Okay, so it's usually quite good thing to do. To either standardize, you can also center them. Centering is non-standardized standardization, so to speak. You just take your scale and you move it so it will be with 0 in the middle. So this seems more robust. How do we interpret this? Well, I had the next slide. We can have a look. The correlations here. Medicine and squared. Extremely strong correlation. Problems with collinearity. And this case, standardized medication and standardized medication squared, no correlation whatsoever. Of course, usually it's not like that, but in this example. Okay, so we get the formula like this. Predicted life satisfaction is 6 plus 0.11 multiplied by standardized medication. So you see I get those from there. Minus 2.46 multiplied by standardized medication squared. Now you might think that, oh, this standardized medication is not significant. Therefore, we remove it from the model. But then you don't have a curve linear associate model anymore. Then you have an exponential model. You have it like this. You don't have a mean or max point. You just have a deterioration with the acceleration. If it would still be negative, that one. I guess it would still be. In order to get a curve, you have to have them both in. So we don't really care that it's not significant here. It's still, we still keep it in the model, because otherwise we don't have a curve. What about this intercept? 6. How do we interpret that? And be careful now. When do we predict life satisfaction to be 6? Well, the general rule is, and it still applies, the intercept stands for the predicted value on the dependent variable when all predictors are 0. But what would it mean in this case for all predictors to be 0? Exactly. Because we have zeta standardized them, therefore 0 is equal to the mean. So if you have a mean level of medication, your life satisfaction is expected to be 6 on the scale from 1 to 7. These values, the sign of these values tells us what the association looks like. In our example, we have a positive coefficient for medication and a negative for the squared term. That means we have an association that looks like this. Inverted U association. So we have some kind of max point here. If you get too much medicine, life satisfaction decreases. If you get too little medicine, also life satisfaction is expected to be lower. So lagom is best, as we say in Swedish, this model indicates. If it would be the opposite, negative x term and positive squared term, then we have an association that looks like this instead. The values on the dependent variable decrease until a certain point, and then they start to increase. If both are negative, we have a decrease with accelerating speed. Both are positive, we have an increase with accelerating speed. Our favorite subject among all comes now. Interactions. What is an interaction? If, for instance, medication and therapy interact in their effect on life satisfaction, what does that mean? If medication and therapy interact in their effect on life satisfaction, it means that the effect of therapy on life satisfaction is different depending on how much medication you receive. So the effect of therapy on life satisfaction is different for different levels of medication. That would at the same time mean that the effect of medication on life satisfaction is dependent on therapy. It looks different for different levels of therapy. That's an interaction. Interactions might look in many complicated ways. You can have curvilinear interactions, but usually we imagine that if there is an interaction, it's a linear interaction. So in this case, we imagine that the effect of therapy on life satisfaction is a linear function of medication. So let's say that x here, x1 is therapy, and x2 is medication. Okay, if we have the original formula here with no interaction term, we say it looks like this. But now, if we say there is an interaction, then we say that this effect, the regression coefficient for the effect of therapy on life satisfaction, is a function of your value on medication. So we have a formula, a function for that coefficient. So if we have linear interaction, we say that the value of that coefficient is C plus D multiplied with your value X on the other predictor, in this case medication. In this formula, B1, the effect of the predictor 1, C is the intercept for the effect. Stands for the effect of predictor, the effect of therapy on life satisfaction when the value on medication is 0. And D stands for how much the regression coefficient for the effect of therapy, how much it changes when medication increases by 1. If we now put in that formula instead of B1 here, that's what I change B1 to the formula there. Keep the rest. And then we do some algebra here. Then we get that predicted life satisfaction is intercept plus a coefficient multiplied by value on therapy plus another coefficient multiplied by value on medication plus a third coefficient multiplied by value on therapy multiplied by value on medication. In this way, we have incorporated a linear interaction into the regression model. So what do we do to test for an interaction? Well, those we already have, values on the first and the second predictor, but we create a new variable. That is the product of those two values, of the values on those two variables. So we put in 3, the first predictor, the second, and their product. We put in all 3 as predictors in regression analysis. And we get 3 regression coefficients, and we have a look at them. And the one we're most interested in is this called D here. If that is significant, it indicates that there is a significant interaction. It indicates that the effect of one of the predictors on the outcome variable looks different between different values on the other predictor. I guess many of you might have seen this, you put in at the interaction, but this is why. But then it, so to speak, gives you the interaction. Yes?
But the same story could have happened also for the B2.
For?
The B2.
Yes. We would get exactly the same if we said that B2 was a function of the value on x1. It would be exactly the same.
And the next question, could we claim that this C is independent effect of x1?
No. It changes by including the interaction term here. Those are no longer as before the independent effects. They now are instead the effect of that predictor when the other one is 0. Yeah, but the interaction is 0 if the other one is 0. If x2 is 0, then of course this becomes 0. If x1 is 0, then this becomes 0. So if either one of those are 0, then always the interaction term will be 0. Okay, so let's have an example here. We have life satisfaction, we have therapy and medicine. So we want to predict life satisfaction from therapy, medicine, and their interaction. So we create this product variable by multiplying those two with each other. In each row we multiply the values, and we get the product variable. Then we put those in, therapy, medicine, and their product, as predictors of life satisfaction. and have a look at the p-value for this interaction term, if it's significant or not. Do you anticipate something from that analysis? Some kind of problem? Therapy and medicine, they only have positive values. Therefore, the higher the value you have on either on them, the higher the product. We anticipate collinearity. It's quite common. Do you have any trick to avoid that problem? We standardize. So I standardize therapy, I standardize medicine. Centering functions just as well. So I standardize them first, and then I multiply them. Because then we don't have this linear association anymore. Not to the same degree, at least. Okay, so above the line, non-standardized predictors. And here we have them standardized. How much of the variance in life satisfaction can be explained by therapy, medicine, and their interaction? 88%. And it's exactly the same. However, does the interaction term add anything, or could we do just as well without it? Is there any significant interaction? Yes. The p-value for the interaction term is significant. And it's exactly the same in both cases. But this model might still seem preferable because we have higher tolerance values. It's not a problem if you only have two predictors and their interaction. Then it doesn't really matter if you standardize them or not. But if you're going to add more variables, then this is to prefer. Then it's more robust. More computationally robust. You see, here we have quite low values, tolerance values. Here they are nice, high and nice. Again, somebody might think like this. Oh, okay, this set of medication is non-significant, so we take it away from the model. But if you do that, it changes the interpretation of this. Then it's no longer an interaction term. It's something else. It is an interaction term if you have both of the original variables in the model. Then it captures the interaction. Otherwise, it doesn't. I saw somebody, for instance, those two become insignificant, like in this case. So they kept only the interaction term and said, there is only an interaction. No, it's not the interaction anymore. It's only a product variable. The product variable catches the interaction if the two original variables are in the model. Otherwise, it doesn't. Otherwise, it's something else. Intercept, 3.7. What does it mean? When do we predict life satisfaction to be 3.7? Notice the difference here, for instance. In the first model, the intercept is minus 0.3, and here it's plus 3.7. What is the difference? In the first model, what does minus 0.3 stand for? Predicted life satisfaction if the values are 0, which means no treatment and no medication. If you receive no treatment and no medication, your life satisfaction is expected to be minus 0.3. And here, if you receive average level of medication, average level of medicine, your life satisfaction is predicted to be 3.7. It's because the value 0 means different things in the two models. Here we see why we get problems with collinearity in the first model, but not in the second one. Let's have a look at this parameter values here. So our predicted life satisfaction is given by this formula. And that's the coefficients here. If I try a few combinations of standardized medication, standardized therapy, so I put like -2, if I put in -2 for zeta medication and -2 for zeta therapy, if I put those into the model, I get that predicted value. Predicted life satisfaction -5.9 on a scale from 1 to 7. And so on. So now we see here, for instance, the intercept, 3.7. It's the predicted life satisfaction. There we have it. If both variables are 0, which means that you receive an average level of therapy and an average level of medication. Let's start here. If zeta medication is 0, and I predict the life satisfaction from 5 different levels of therapy here. So we see if we go from -2 to -1, life satisfaction increases from 2.6 to 3.18. And then if it increases one more, the therapy, life satisfaction increases to 3.7 and so on. At this line. If you had a look at this, every increase here is equally big. It's an increase by 0.521. If we have a look at our coefficients here, what do we see? We see that the coefficient for zeta therapy is 0.521. Exactly the same. And that's not a coincidence. So what does this coefficient stand for? The coefficient for zeta therapy, 0.521. What does it stand for? It stands for the effect of that predictor of zeta therapy on life satisfaction if zeta medication is 0. Which in this case means that you receive an average level of medicine. If you receive an average level of medicine, your standardized value on medication is 0, then every increase in therapy by 1 standard deviation, because that's what it means, is associated with an increase in life satisfaction with 0.521 points on the scale from 1 to 7. Let's have a look here. Zeta therapy 0. So we look at people who receive average amount of therapy. And then we have a look at 5 different levels of medication here. And we see that for every increase in medication, the life satisfaction increases. How much? Well, it increases with 0.41. And that's exactly the same value as there. So given that your value on zeta therapy is 0, you receive an average amount of therapy. An increase in medication by 1 standard deviation is associated with an increase in life satisfaction with 0.41 points. So those two coefficients stand for the effect of that coefficient, that predictor on the outcome, if the other predictor is 0. What happens with the effect of zeta therapy here when medication increases? Because we have a significant interaction term, it indicates that the effect of therapy on life satisfaction changes if we change medication. So here I have calculated the effect of therapy on life satisfaction for different levels of medication. So if medication increases from -2 to -1, the effect of therapy goes from 4.4 to 2.4. If we increase medication even further, the effect changes even further. In this case, it decreases. If we calculate the difference between each step here, it will be, can you guess? minus 1.94. Every decrease here, every change is minus 1.94. That means that if medication increases by one standard deviation, the effect of standardized therapy on life satisfaction, the coefficient for that effect, decreases by 1.94. So that is the change in the effect of therapy on life satisfaction when medication, in this case standardized medication, increases by 1. Let's have a look at the other way. The effect of medication. Here it is. If therapy is -2, the effect is 4.3. If therapy is -1, the effect is still instead 2.3, and so on. Can you guess how much the effect of medication changes here when therapy increases by 1? It's exactly the same. Minus 1.94. So the interaction term, the coefficient for the interaction, stands for how much the effect of one of the predictor on the outcome variable changes when the other predictor increases by 1. That's what the coefficient for the interaction term stands for. In this case, the interaction term is negative and significant. What conclusion do we draw from that? If we express it more in words. If medication increases, what happens with the effect of therapy on life satisfaction? It decreases. And given that you receive enough medicine, the effect even becomes negative. So therapy is good for life satisfaction, given that you don't get too much medicine. And the effect of medicine on life satisfaction? Is it good for life satisfaction to receive a lot of medicine? Yes, but only if you don't get too much therapy. If you have a low value on one of the predictors, the other predictor has a positive association with life satisfaction. But if the value on the other predictor increases, the effect decreases and eventually even become negative. That's what the negative interaction term here indicates. And it's significant. Good morning. Welcome to this day about regression analysis. So I put together a content like this two main headings here, simple and multiple regression analysis.